Hello, and welcome to Controllers Tech. In today's session, we will continue working with the STM32 IoT series using the ESP8266 Wi-Fi transceiver module. In the earlier parts of this series, we learned how to connect the STM32 with the ESP8266 module, how to link the module and the board to a Wi-Fi network, and finally how to send data to the ThinkSpeak cloud using a TCP connection. Now, we're starting a new mini-series that focuses on the MQTT protocol. In this mini-series, the STM32 will act as an MQTT client. This means it will have the ability to both publish messages to topics and subscribe to topics in order to receive messages. I'm calling it a mini-series because the MQTT protocol will be covered in about 3 to 4 parts. While writing the code, I will also explain the protocol details step by step. Since the protocol has several elements, it will take a little time to cover everything properly. In today's video, we will specifically focus on 2 important parts: the connect packet and the publish packet sent by the client. We will go through the packet structure, understand how these packets are created, how to send them to the broker, and finally how to handle the acknowledgement messages that come back from the broker. To make things easier, I have prepared an MQTT document that explains these concepts. This document only contains the most important details that we will actually use in this MQTT series, while skipping the extra parts that are not relevant right now. If you would like the complete version of the document, you can find the link in the description of this video. We will use this document later in a video when I explain the MQTT functions in more detail. Before we move forward, please make sure you have already watched the first part of this series, because from this point on, I will assume that the STM32 is already connected to the internet. Now, before diving into the coding, let's set up a few things that we will need. First, we require another MQTT client to monitor the messages that will be published by STM32. For this purpose, I will use MQTT Explorer, which is a simple and useful tool. You can download MQTT Explorer directly from their official website. I already have it installed on my computer, so we will use that here. The next requirement is a broker. You can use any MQTT broker of your choice, but in this video, I will be using the HiveMQ public broker. To access this broker, simply visit hivemq.com. Under the MQTT section, click on MQTT public broker. Here you will see the HiveMQ public broker page. Click on the Connect button, and it will display the broker details. From this, we only need 2 things: the host address and the TCP port. I will be using the TCP port because it allows for an easy connection to the broker without needing certificates. Although this method is not secure, it is simpler to use when starting out. Don't worry, we will cover secure MQTT communication using SSL certificates in one of the future videos. Once you have the host and port, go back to your MQTT client and enter those details in the respective fields. After that, click on the Advanced section to add topics. I have already added 2 topics for this client so that it can publish and subscribe to them. Adding a topic is very simple. Just type the topic name and click Add. Once you do this, the client will automatically subscribe to that topic. Now, any messages that are published to these topics will appear right here in the MQTT Explorer client. Finally, after adding the topics, click on Connect to establish a connection between the client and the broker. At this point, one of our clients, the MQTT Explorer, is ready. Now, the next step is to prepare the other client, which is our STM32. I'm going to continue with the project that we created in part 1 of this IoT series. As you can see here, the project from part 1 is already loaded into the IDE. To keep things organized and avoid any confusion in future videos, let's rename this project from part 1 to part 3. While renaming, make sure to also check the option to update references so that all link files are updated automatically. Alright, the renaming is complete. All the references that mention part 1 are now updated to part 3. The only exception is the debug configuration. Let's delete it because it will be automatically regenerated the next time we launch the debugger for this project. Now, we also need to delete the ESP8266 library files from the project. That's because we are going to copy new files that contain the updated MQTT-related functions. I'm copying those new files here now. You can download these files yourself from the link provided in the description of this video. Let's open the ESP8266 source file and see what has changed. This file still contains the ThingSpeak function from the previous video. Because of that, you will notice a printf error for floating point values. We don't actually need the ThingSpeak function anymore, but instead of deleting it, I have decided to leave it in the file. To fix the printf error, we just need to enable float printf support in the project settings. Once that is done, let's review the source file again. Here we have several functions already explained in the earlier parts of this series. ESP init, used to initialize the ESP8266 module. ESP connect Wi-Fi, connects the module to a known Wi-Fi network. ESP get connection state, checks the current connection status of the module. ESP send to ThingSpeak, sends data to the ThingSpeak cloud. Now, for the MQTT implementation, I have added some new functions. ESP MQTT connect, to connect the module to an MQTT broker. ESP MQTT publish, to publish a message to a topic. ESP MQTT ping, to send a keep alive ping to the broker. Apart from these global functions, there are also some static functions specifically for MQTT communication. For example, we now have ESP send binary, which will be used to send MQTT commands. Normally, we use ESP send command for sending ASCII-based AT commands, but since MQTT requires binary data, a new function was necessary. You'll see why this is important very soon. Another new function is ESP MQTT build connect, which builds the MQTT connect command that allows the client to register itself with the broker. Let's now go through these functions in detail, starting with ESP MQTT connect. This function is used by the STM32 client to connect to the broker. Its parameters include the broker address, the connection port, the client ID, which identifies this client to the broker, a username and password if required by the broker, and finally, the keep alive time in seconds. At the beginning of this function, we send the AT plus SIP start command. This command opens a TCP connection with the broker at the given address and port. If the broker accepts the connection, it responds with a connect acknowledgement. We already saw something similar in the previous video when we connected to the ThingSpeak cloud. Once the connection is established, the next step is to send the connect packet to the broker. This packet officially registers the STM32 as an MQTT client. Before sending it, though, we first need to build the connect packet using the function parameters we just discussed. Let's understand how this connect packet is structured with the help of the MQTT document. Every MQTT control packet is made up of three parts. A fixed header, which is common to all MQTT packets. A variable header, which is present in some packets. A payload, which is also present in some packets. Let's now take a closer look at the MQTT control packet for the connect command. The fixed header in this packet is 2 bytes long. The first byte represents the packet type, in this case, the connect packet, which has a value of 0x10. The second byte represents the remaining length of the command. The remaining length indicates the total size of the variable header plus the payload. Inside the build connect function, we start by storing the value 0x10 to represent the connect packet type. The remaining length is skipped at this stage because we don't know it yet. This position will be filled later after the entire control packet is built and we know its exact length. With that, the fixed header is complete. Next, we move on to preparing the variable header. The variable header begins with a protocol name. To store this, we first write 2 bytes, 0x00 and 0x04, which indicate the length of the protocol name. After that, we store the actual name itself, which is MQTT. In the build connect function, you'll see this being done. First 0x00, then 0x04, followed by the 4 characters of MQTT. Next, we store the protocol level. Since we are using MQTT version 3.1.1, the protocol level value will be 0x04. This is also handled in the build connect function. After that, we set the connect flags. These flags configure different options for the behavior of the MQTT connection. To enable a feature, we set the corresponding bit in this byte. For example, if the broker requires a username and password, their respective flags will be set here. Other flags, such as retain, quality of service, or will parameters, are not covered in this series, so we will skip them for now. However, one important flag is the clean session bit, which must always be set. This ensures that the broker does not store any previous session information and starts fresh each time. If the username and password are included in the function parameters, their flags will also be enabled here. Once the connect flags are set, we define the keep alive interval. The keep alive is a time interval defined by the client that ensures the TCP connection with the MQTT broker remains active. It's 2 bytes long, so we must split the 16-bit parameter into 2 bytes, sending the higher byte first, followed by the lower byte. That completes the variable header section of the connect packet. Now we move on to the final part, the payload. The payload may contain several items, such as the client ID, will topic, will message, username, and password. But in every case, it must at least include the client ID. The client ID comes from the function parameter. To store it, we first calculate its length. Then, we send 2 bytes to indicate that length, followed by the actual ID data. If the function parameters also include a username and password, these are added in the same way. First the 2-byte length field, and then the data itself. Once the entire connect packet is built, we now have the correct total length of the packet stored in a variable. We then go back and place this length value into the fixed header, but with one adjustment. We subtract 2 from it. This is because the 2 bytes of the fixed header itself are not included in the remaining length field. Instead, that field should only represent the combined length of the variable header and the payload. Finally, the build connect function returns the total length of the entire packet. This includes the fixed header as well, so we know the complete size of the connect packet at the end. After building the connect packet, the next step is to inform the ESP module about how many bytes we're going to send. We do this using the AT plus SIP send command. When this command is sent, the ESP responds with a greater than sign, which indicates that it is now ready to receive the data. At this point, we send the entire connect packet using the ESP send binary function. This function takes the following parameters: the control packet we want to send, the length of the control packet, the expected response from the ESP, and the timeout value in milliseconds. Once the expected response is received, it means that the STM32 client has successfully connected to the broker. Now, let's look at a quick example to understand how these commands appear in practice, and also why we can't use our regular ESP send command function to send MQTT packets. Here is an example of an MQTT connect packet without a username and password. The fixed header comes first, containing 2 values: the packet type 0x10 and the remaining length, which in this case is 23 bytes. These 23 bytes represent the total size of the variable header and payload combined. The variable header begins with 0x00 and 0x04, which indicate the length of the protocol name. This is followed by the actual protocol name, MQTT, the protocol level 0x04, the clean session flag, 0x02, and the keep alive time of 60 seconds. Next comes the payload. Since we are not using a username and password in this example, the payload only includes the client ID. The packet first stores the 2-byte length of the client ID, followed by the actual client ID itself. This gives us the final connect packet in string format. Now notice something important. This packet contains a 0x00 byte. Our regular ESP send command function relies on strlen function to calculate the length of the command string. However, strlen function treats 0x00 as a terminating character. Because of that, it would assume the packet length is only 2 bytes, which is incorrect. This is exactly why we created the ESP send binary function. Instead of calculating the length inside the function, we pass the packet length directly as a parameter, ensuring the entire packet, including the 0x00 bytes, is sent correctly. Let's now look at another example where we connect to the broker using both a username and password. Most parts of the connect packet remain the same, but there are a few key changes. The fixed header now shows a larger remaining length, since it must also include the size of the username and password fields. In this case, the remaining length becomes 38 bytes, assuming the username is user1 and the password is pass1. The variable header is almost identical to the earlier example. The only difference is in the connect flags. Here, we need to enable the username and password flags along with the clean session flag. This makes the connect flags byte equal to 0xC2. Finally, the payload includes 3 items: the client ID, the username, and the password. For each of these fields, we first send the 2-byte length, followed by the actual data. The result is our complete MQTT connect packet with authentication. To summarize, this packet consists of 2 bytes of fixed header, 10 bytes of variable header, and 26 bytes of payload. Together, they form the full connect packet containing the client ID, username, and password. When we send these connect packets to the broker replies with a connect acknowledgement. The fixed header of this acknowledgement packet contains the acknowledgement packet type, which is 0x20, and the remaining length, which is always 2 bytes. The variable header of the acknowledgement is also 2 bytes long. The first byte contains only the session present flag, while the second byte is 0x00. If the session present flag is set to 0, that means the connection request has been accepted by the broker. So this is what the final connect acknowledgement packet looks like in the case of a successful connection. And with that, our MQTT connect function is complete. Now that the client is connected to the broker, it can start publishing messages to any topic. For this, we use the MQTT publish function, which takes the following parameters: the topic name, the message itself, and the quality of service level. To keep things simple, I will assume that the quality of service is always 0 throughout this series. Just like the connect packet, the publish packet is also made up of a fixed header, a variable header, and the payload. Let's quickly go through this with the help of the document. The first byte of the fixed header contains the publish packet type, which is 0x30. Along with it, there are flags such as duplicate, quality of service, and retain. Since we are assuming all these flags are 0, the fixed header becomes 0x30. This is followed by the remaining length, which specifies the size of the variable header and payload. Next is the variable header, which consists of the topic name. Here, we first send the 2-byte length of the topic name, followed by the topic name itself. Finally, we have the payload, which is simply the message the client wants to send. Unlike the topic name, the payload does not include a length field. It only contains the message itself. Once the total packet is ready, we calculate its length and store it in the remaining length field of the fixed header. Here is an example of a published packet with quality of service set to 0. As you can see, we first have the fixed header, then the variable header with the topic name, and finally the message and the payload. This completes the published packet. Since the quality of service is 0, the broker will not send back an acknowledgement for this published packet. After preparing the published packet, we again inform the ESP module about how many bytes we're going to send by using the AT plus SIP send command. The module will respond with the greater than sign, showing that it is ready to receive the data. Next, we send the publish packet, and then wait for the send OK acknowledgement from the ESP module. Keep in mind that there will be no acknowledgement from the broker in this case, so we must rely on the acknowledgement coming from the module itself. We will talk about the ping request in the next video, but before that, let's test the connect and publish packets we just created. I have also added a function that allows us to check the current connection status with the broker. The command used is 8t plus SIP status, which tells us if the module is still connected. If the connection is active, the module responds with status 3. This check can be performed before publishing data to a topic, just to ensure that the connection with the broker is still alive. Now let's move on to writing the main code. After the ESP module is successfully connected to the Wi-Fi network, we will call the ESP MQTT connect function to establish a connection with the broker. In this function, we need to provide the following details: the broker address, the port number, the client ID that we want to assign to our STM32, username and password if the broker requires authentication, and finally, the keep alive interval in seconds. If the connection is successful, the module will respond with an OK. Next, I will publish messages continuously inside the while loop. Before publishing, we first check if the module is still connected to the broker. If the connection is valid, we then call the ESP MQTT publish function to send data to the topic. For this example, I will publish to the topic controllers tech/test1, and the message will remain the same each time. The quality of service will be 0. Let's build the project now. The build is successful, which means we are ready to flash it to the board. The hardware connections remain the same as in the first part of this series. The RX pin from the adapter is connected to PA0, UART4TX. The TX pin from the adapter is connected to PA1, UART4RX. The ESP adapter is powered by 5 volts from the STM32 board itself, but make sure that the USB cable is connected to the development board. The ST-Link V2 only provides a 3.3 volt supply to the board. So if you want, you can use an external 5 volt supply for the adapter, but in that case, remember to connect the ground of the external supply with the STM32 development board's ground as well. The PA9 UART1TX pin is connected to the RX pin of the FT232 adapter. Since we only need to send logs to the console, connecting just the TX pin is enough. Now, let's flash the project to the board. Once done, open the serial port on the console at a baud rate of 11.5/200 to view the logs. The initialization process begins. At the same time, I have MQTT Explorer running as another client connected to the same broker, subscribed to the same topic. This allows us to verify the messages being published by the STM32 client. You can see from the logs that the broker has accepted the connection and data publishing has started. The message appears on the MQTT Explorer client under the topic controllers tech/test1. The STM32 has published another message, and it has also appeared in MQTT Explorer. Since the message content is the same each time, it looks identical. But if you check under the main topic controllers tech, you can see that there are now 3 messages in total. This confirms that the STM32, as an MQTT client, is able to connect to the broker and publish messages to a topic successfully. Now let's modify the main function so that the STM32 sends different messages each time. First, define a count variable that will increment with every loop. We also need a count array to store the value of this variable in character form. Inside the while loop, use sprintf to convert the count value into a string and store it inside the count array. Then increment the count variable, so each iteration produces a new value. Finally, pass this count array as the message in the ESP MQTT publish function to publish it to the topic. Let's build and flash the project again. I'll clear the old data from MQTT Explorer for a fresh start. Now, the STM32 client has successfully connected to the broker and started transmitting updated values. You can clearly see the new values being published to the topic in MQTT Explorer, proving that the setup is working perfectly. So, the STM32, acting as an MQTT client, is able to connect, publish fixed messages, and also publish dynamic messages to the broker. In the next video, we will cover why and how to send a ping request to the broker. After that, I'll show you how to publish messages using routers, making the process more practical and efficient. And in the video following that, we will learn how to subscribe to a topic and make use of the data received from it. That's it for today's video. I hope the explanation was clear. You can download the project from the link in the description. If you have any doubts, feel free to leave them in the comments. Keep watching and have a great day ahead.